Good morning, everybody. There's actually no such thing as a good morning, but it is morning, so there's that. I am a night owl, so I am quite out of my element at this stage in the game. But hello to all of you. I'm AJ ONeal. I guess we'll go over me as the 0th element in this list. So this is AJ's BYU 2022 lecture series. Assuming, yeah, woo! Assuming that there's at least 3 parts here, and then maybe more to come. We'll see. So I want to make sure everybody has the link. So if you want to look at these slides, you can. It is very long. I apologize for that. Not my fault. Someone else grabbed the name that I wanted to get just Beyond Code, but that was taken. So I had to take beyondcodebootcamp.github.io. And then /prezos/BYU 2022. And if you're familiar with GitHub, which you better be, then you can reverse engineer from that how you can get the source code for all my slide files. So we're going to have maybe 3 parts today. This is a 4-hour session that we're doing. I'm not exactly sure how that's going to work out. I can talk and ramble a lot, but I'm assuming we're going to have a lot of time to discuss and break and whatnot, but I can make up material all day long. Don't worry if it comes to that. So the first thing that let me not go into these bits yet. I just wanted you to have the links. These are the links to the presentations. Now, and if you're interested in what I use to create the slides, it's Da Boomer's Markdown Slides. So this is me. You can kind of visually authenticate that. I'm the same guy in the picture, therefore I am me. AJ ONeal @_BeyondCode if you want my no-nonsense tweets, which is not very many of them. Twitch.tv, CoolAJ6 if you want to watch my live streams and hear the unfiltered nonsense. And then me, I am a Golang engineer. I'm Russ curious, a Zig aficionado, and with Node, well, it's complicated. Yeah. So I'm a technophobic technologist. I'm glad to see that there are a lot of people who have features of seasoned individuals in the room, which means we probably have a healthy dose of skepticism from people who have seen the wheel of time turn. I'm a dangerous wrong thinker. You'll probably never see me at a major conference. And I'm an equal opportunity offender. The only COC I abide by is the creeds of craftsmanship. JS Lent will hurt your feelings. Are you familiar with this? Douglas Crockford? Good. AJ will hurt your feelings. So I want to get that out of the way. Also, if you want to take notes and you don't have something to take notes with, I have a tool that I wrote that I use for taking notes that you can optionally log in with GitHub. I don't know what happened there. Optionally log in with GitHub and sync encrypted notes, which you probably have no use for. But if you do, this is my note-taking tool. It's not very good, but it's there. It's better than nothing for sure. And then we go on to, I think, yeah, that's another. I did need to say actually why you should listen to me. Because because I say some things, maybe. Yeah. So I'm the leader of the Rust meetup. I'm the leader of the Utah Node.js meetup. I don't really frequent the Golang meetups as often as I would if I weren't busy running the other 2. And I'm also one of the longest running hosts on the longest running JavaScript podcast, which is JavaScript Jabber. The reason that you shouldn't listen to me is that I primarily work with startups, and they ask me to come here to speak about how to teach you about enterprise software, and I don't know the first thing about that. So, oops. But with that out of the way, let's go ahead and open up to on software engineering. Or first, do we have any questions thus far? Remember, I can't see well early in the morning, so you'll have to be more audible. My eyes are still blurry. Okay. I don't think I hear anyone. Okay, so the reason we're going to talk about software engineering first is because it's my favorite topic. Also, if I don't get your buy-in during this phase, then you can pretty much just leave and go elsewhere because you won't care about any of the rest of what I have to say about Node. Because there's certain principles that if we fundamentally don't align on, then you're just going to learn about the opinions of someone you don't agree with. So we're going to take the bitter pill first and then see if the spoonful of sugar follows or not. By the mouth of 2 or 3 witnesses. So this section is maybe less of me talking and more of listening to people that are older and more wizened than I am. So I haven't done a presentation in this style before. We'll see how it goes, and if it turns out terrible, we'll change tactics. But my goal is actually to convince you that the ideas that I have brought down from the ether have come from glorious messengers, as it were. So software engineering is programming with respect to time and across people. Now, this is me paraphrasing Rob Pike as quoted by Russ Cox, who's paraphrasing Titus Winters. And you'll see exactly what that means momentarily, but this is the core thing that we need to buy into together, or you're going to have to, that's what we got to do. So I am actually going to let you hear from Russ Cox for about a minute or so, and then Titus Winters, and then some other people. We're going to see what they have to say, and you can ask questions or add commentary. I don't know. This is kind of weird, but I decided to do it this way because they're smart people and they are more eloquent than I am.
What is software engineering? How is software engineering different from programming? I like the following definition, which I borrowed and adapted from Titus Winters. Software engineering is what happens to programming when you add time and other programmers. Programming means getting a program working. You have a problem to solve, you write some Go code, you run it, you get your answer, and you're done. That's programming, and that's difficult enough by itself. But what if that code has to keep working day after day? What if 5 other programmers need to work on the code too? What if the code must adapt gracefully as requirements change? Well, then you start thinking about version control systems to track how the code changes over time and to coordinate with the other programmers. You add unit tests to make sure that the bugs you fix are not reintroduced over time, not by you 6 months from now, not by that new team member who's unfamiliar with the code. You think about modularity and design patterns to divide the program into parts that team members can work on mostly independently. You use tools to help you find bugs earlier. You look for ways to make programs as clear as possible so that bugs are less likely. You make sure that small changes can be tested quickly, even in large programs. You're doing all of this because your programming has turned into software engineering. Nearly all of Go's distinctive...
Okay, so that's Russ Cox. Now we're going to hear from Titus Winters, who's going to explain it slightly differently, but still eloquently, and hopefully cements the idea in.
The things that you work with. But first, we can't really look at those practices of software engineering without some working definition of what is software engineering. We all know what programming is, but what is the difference between these two things? Why do we have 2 words for these concepts? Software engineering, to me, is programming integrated over time. I'll put this another way. A programming task is, oh hey, I got my thing to work, and congratulations. Programming is hard. And a lot of the time, the right answer to a problem is, I'm going to go write a program, solve that problem, and be done. Right? That's great. No judgment, right? Totally fine. Engineering, on the other hand, is what happens when things need to live for longer and the influence of time starts creeping in. The library that you used has a new version. The operating system you developed for has been deprecated. The language you wrote in has been revised and you need to update. The requirements have changed and you need to add new features. Other developers are working on it. You're moving to a new team. You're moving to a new computer. Your hard drive died. Time happens. Things change. How you handle that and how you keep your programming working is engineering. It may bleed into the programming itself as you plan for change within the structure of the code, or it may be entirely layered on top when your quick one-off hack becomes enshrined as a critical feature of your team's toolset.
Any thoughts or comments on that right there? I hope that that's fairly non-controversial stuff. All right, I'll move right along then. So now I would like to present to you some of the most important archaeological documents of the 22nd century. I've been collecting these at creedsofcraftsmanship.com, so if you want to check them out and more, they are available there. Pretty much everything that I'm referencing is other material is available there. Right now it's just a GitHub issue that I keep on adding things to, but it serves its purpose. And I like to make things memorable, hence I got the domain for it, so it's easy to communicate with people. So one of these, and I'm not going to go into these in depth right now. We may circle back around to these later. But one of these is the Zen of Python. So the languages that I love, one of the characteristics that is in common with all the languages that I love is that they have strong leadership that has opinions that seem to reflect the same ideas over and over again about this concept of software engineering. How do we make software withstand the test of time and people? So I'm going to rattle these off. I'm not going to give any explanation. I have another talk that you can watch. It's linked to at creedsofcraftsmanship.com if you're interested in seeing my full interpretation of these. And like I said, we may come back to these later, but I'm just going to rattle these off along with a few others just to kind of get these ideas out there. So beautiful is better than ugly. Explicit is better than implicit. Simple is better than complex. Complex is better than complicated. Flat is better than nested. Sparse is better than dense. Readability counts. Special cases aren't special enough to break the rules. Although practicality beats purity, errors should never pass silently unless explicitly silenced. Actually, I didn't put the full stop on there. Although practicality beats purity, stop. Errors should never pass silently unless explicitly silenced. In the face of ambiguity, refuse the temptation to guess. That's one of my favorites. There should be one and preferably only one obvious way to do it, although that way may not be obvious at first unless you're Dutch. So small commentary, core members of the Python team were Dutch. So some cultural understanding was shared. Now is better than never, although never is often better than right now. If the implementation is hard to explain, it's a bad idea. If the implementation is easy to explain, it may be a good idea. Namespaces are one honkin' great idea. Let's do more of those. Similarly, we have the Go Proverbs. Don't communicate by sharing memory. Share memory by communicating. And I had the years on these. Python's from Zen of Python's 2004. This is actually from 2015, but the way that my window got condensed when it went to 1980 by the 1080p, chopped it off at the bottom there. But anyway, concurrency is not parallelism. Channels orchestrate, mutexes serialize. The bigger the interface, the weaker the abstraction. Now, you that have been dealing with Java and Kotlin and C++, I presume to some degree, I hear most of you came from a Kotlin background before this. I think that should become clear to you if it isn't immediately clear just on its face. Make the zero value useful. Marker interface, empty marker interface says nothing. Go thumped style is no one's favorite, yet go thumped is everyone's favorite. Go format. A little copying is better than a little dependency. Syscall must always be guarded with build tags. Cgo must always be guarded with build tags. Cgo is not Go. Some of these are kind of Go specific, but you can apply them to other languages as well. With the unsafe package, there are no guarantees. Clear is better than clever. Reflection, meaning metaprogramming, is never clear. Errors are values. Don't just check errors, handle them gracefully. Design the architecture, name the components, document the details. Documentation is for users. Don't panic. Moving on to the Zen of Zig. This is from 2017. It's actually still being refined. Communicate intent precisely. Edge cases matter. Favor reading code over writing code. Small interjection, which we'll probably come back around to this again. You will write code once, you will read it for the rest of its existence. So, hence that. Only one obvious way to do things. You can kind of tell these have an ancestral history back to the Zen of Python. I believe that the fact that the Go Proverbs has 19 stanzas is a nod to the 19 stanzas of the Zen of Python. Runtime crashes are better than bugs. Compile errors are better than runtime crashes. Incremental improvements, avoid local maxims, reduce the amount one must remember. I'm going to come back to that. Actually, that's a very large part of this. Focus on code rather than style. Resource allocation may fail. Resource deallocation must succeed. Memory is a resource. Together, we serve the users. And then this one, it cannot quite reach that claim yet because it's still in draft mode and it's by me and no one knows who I am. But I will add in my own work in progress bit here. Perfection is achieved not when there is nothing more to add, but when there is nothing left to take away. Antoine de Saint-Exupéry. Return something or return nothing. And these are geared more towards JavaScript in particular. Return await or await without return. Let errors bubble until they burst. Correct or classify, but do not catch. Gatekeepers at the gates, doorkeepers at the doors. No worthless abstractions. Abstractions should be deep, as per John Ousterhout. Probably pronouncing that terribly. But by the third or fourth time, you should know what it is. Optimize for the happy path, not for exceptions. When it is broken, it is the right time to fix it. Chinese fortune cookie I got once. This is true. I thought that was very profound. The constraint of the medium defines the art. A BYU alumni, Soraya Bunnell. Anything goes is not a workable constraint. If it sounds cool, don't do it. And I've actually added a couple more since I put this in here, but I won't go to them as of right now. So, to take away, I'm going to try to summarize this in two key bits. What am I driving at about this software engineering thing that I'm trying to get you to buy into before we talk about Node and JavaScript? The biggest one is that less is more. And again, this quote, I learned of this from Douglas Crockford. Have y'all watched the Douglas Crockford lecture series, any of you? Okay, I highly recommend it. It is 8 or 9, I think it's 9 videos spanning a decade. He did the first one for Google. He did the next 8 for Yahoo, and then he did the final one independently. So I guess that actually, off by 1 error, whatever. We could say it was 0 indexed. But anyway, I think that especially if you're going to be programming in JavaScript, it's very good to kind of see the history of things and to watch Crockford's opinions change over the years. As he is doing these various presentations, he'll sometimes say, I used to say this, but I realized that was wrong. That's a bad idea, and I don't do that anymore, and now I do this instead. So anyway, but this concept of perfection is when we have identified what is most critical, and we get rid of the things that are not critical because they're extra mental burden, and they are extra things that have to hang around and be maintained or be understood or be communicated. So we want to get rid of the things that are not the things that are the essential bits. So I will do a little clip from him sharing the same thing, or maybe I cut it off.
In one of them, he wrote what I think is one of the best sentences ever written. He said, "It seems that perfection is attained not when there is nothing more to add, but when there is nothing more to take away." He was writing about the design of airplanes, but it seems to talk about everything which combines discipline and creativity. And I hear this quote being used all the time in architecture and in design and everything, but I think it has a particular application to programming, because we have this real connection with perfection more than any other craft. Our programs have to be perfect. And if our programs are not perfect in every way, bad things happen. And he gives us some insight as to how perfection is attained. It's not by adding things, it's by taking things away. And it occurred to me that this should also apply to programming languages, that we can make our programming languages better by taking away things. So that leads to the idea of good parts, where a language can be made better not by adding things, but by removing things.
Also, to add a little bit of credibility to what he's talking about with our software must be perfect, it sounds somewhat maybe like a euphemism or an exaggeration, but it isn't necessarily. If you're building a social app, yeah, who cares? But how many of you are aware of the plane that crashed? What was it? Was it about 2 years ago or so from a software bug? It was big in the news because basically the guidance system, the plane basically just gave the pilot the wrong information, so the pilot made the wrong choice and everything would have been fine if the pilot was just manually at the stick. But the software glitched in some fashion that caused it to give bad information to the pilot and start making autocorrections that the pilot was perfectly capable of overriding and correcting, but because of the miscommunication, the plane goes down. Now that's thankfully extremely rare. One of the cases that wasn't so rare was the Toyotas. I don't know how many of you have noticed when you touch the brake in your car, it has nothing to do with your foot. The first time I got one of the newer cars, because I've stuck with the older cars for a long time, I like older things better most of the time, but in my Prius, there's no relationship between my foot on the brake and what the car does in a exact sense. It's software, right? So I put my foot on the brake, and then the computer says, okay, do I want to really brake, or do I want to recharge the battery, or what is it that I want to do? And so at different times of day, under different weather conditions, not in the way that is an effect from the road or from the driving conditions, but from what the car thinks about what it should do, it will decide how hard to brake or not. Has anybody else noticed this when you're driving your car, that the brake is responsive via software? Because the cars are not connected to brakes via brake lines anymore. They're connected via software. And there was a problem with numerous Toyotas where they would lock up. And if you have does anybody have an electric car? Okay, so most of you are probably not that familiar with these problems then. Although the brake one, even in the non-electric cars, that is more and more commonplace. But the cars would lock up and become non-responsive, and the only way to get them to start responding to the brake and the other controls appropriately would be to turn the car off and turn it back on again. Have you ever had your electric vehicle just stop and... Okay, my wife had this happen where the electric car stalled. What do you do when an electric car stalls? How does that even happen? Thankfully, it was just coming right out of our neighborhood, and it was no big deal. But it's freaky. It's freaky, some of the things that go on in the world. So, although no, in the general case, our software doesn't have to be perfect. In the broad sense of systems that are critical systems, also I imagine most of you I've heard in some class or other about the X-ray system back in, I don't know, the 60s or 70s. It wouldn't have been the 60s, it must have been 70s or 80s or something. There was an X-ray system that if you press the buttons too fast, the input wouldn't update, so it would display on the screen that the X-ray value was at 10, but actually you'd pressed it up to 12 or 15. And so there's lots of things in software. If you don't get it right, then it is deadly. So there's that. As Bill Gates would say, oh, he died, so there's that. And if you don't get that reference, don't worry about it. It did happen. So one of the issues that exists in the software community at large is we want to add more features, but features add complexity. We want simplicity because our brains are small, because we're human. And features hurt readability. We want readability. Readability is the most important feature of a programming language because readable means reliable. So another few minutes here from our good friend Rob Pike.
If there's really a lot of features, you may look at the line of code, write it one way. Ooh, I could do something different. I could use this feature. I use that feature. You might even spend half an hour playing with a few lines of code to find all the right ways you could use different features to make the code work a certain way. And it's kind of a waste of time to do that. But worse, when you come back to the program later, you have to recreate that thought process. You not only have to understand this complicated programming language doing whatever it's doing, you have to understand why the programmer, who might be you, decided that this was the way to approach the problem from the feature set available. And that is just, I think, bad engineering. The summarization of this is the code is harder to understand simply because it is using a more complex language. You want to have just one way, or at least fewer, simpler, easier to understand ways. So in other words, features add complexity, we want simplicity. Features hurt readability, we really want readability. And readability is, by my opinion, the most important feature of a programming language. Because readable means reliable. If you can read the code and know what it means, then it's easier to understand, it's easier to work on, it's easier to extend, it's easier to fix when it breaks, it's easier to understand why it's broken. These are all good things, and that is why readability is so important. If the language is complicated, on the other hand, you have to understand more to understand even where to start working on the program. And you have to understand a more complicated model in which the program is being written. These cost time and make the language harder to use. But there's a trade-off. Obviously, making more features in a language gives you more fun things to play with. And so there's a fundamental trade-off in Go that was made in a different direction from most other languages. And the trade-off is, what do you want? A language that's more fun to write in or easier to work on and maintain? And for the most part, the decisions in Go about what went in were about long-term maintenance, and in particular in the context of large-scale programming, although that's a little off the topic today.
So all of these languages are evolved by adding features. That means they're becoming more complicated. Their complexity is growing while they're simultaneously becoming more similar to one another. I would summarize that as bloat without distinction.
And there are many ways about it. Last year, about May, I think, I went to a conference hosted by Microsoft called Lang.next. And I saw a number of actually quite interesting talks, many of which were the leaders of a particular language talking about a new version that was coming out, like JavaScript, PHP, C#, and so on. And I really was struck by one thing about these talks and these languages, which is most of the talks consisted of features being added by taking something from another language and adding it to this one. So, JavaScript's getting classes and that kind of thing. And I realized that what's happening is all of these languages are turning into the same language. There's a concept called language relativity. As I said, these languages are evolving by adding features. That means they're becoming more complicated. Their complexity is growing while they are simultaneously becoming more similar to one another. And that's a very strange situation for a field to be in. I would summarize that as bloat without distinction.
All right. So another principle of how can we reduce complexity less is more, is to favor composition over inheritance. Now, I realize that a lot of the things that I'm sharing have tie-ins to Go. That's for two reasons. One, because the Go authors are some of the most seasoned veterans in the language creation industry. Between the 3 or 4 of them, they've created half a dozen languages throughout the space of time, so they are very well respected. So it's not just about Go itself. These are things that they were identifying as problems when they got together and created Go. And the next person is also going to reference Go, but this is not a Go programmer by any means. This is someone who's deep into the functional space. And he's gives an explanation of what this composition over inheritance means. And again, if you're coming from C++ or Java or TypeScript, there's a prevailing wind that is to abandon object-oriented design in favor of inheritance-oriented design, which is kind of a, what do you call it, when something comes in the door unannounced. You think you're getting one thing, but you end up with another. You're being told we're going to be object-oriented programming, but instead everything's inheritance. So here's a little snippet on that.
Found in other paradigms.
So this, of course, led to the question of, what are the uniquely OO features? I mean, I can think of a few that get talked about as sort of canonical OO features, like encapsulation maybe, inheritance, objects, methods. So I kind of started to investigate these. So inheritance. This breaks down into 2 categories. One is what people call interface inheritance. This is basically just another term for subtyping. Of course, subtyping is found in all sorts of languages, so that's definitely not uniquely OO. The other one is implementation inheritance, which most people just call inheritance, but I have encountered people who want it to be more specific. So for the rest of this talk, whenever I say inheritance, I mean implementation inheritance. Interesting thing about implementation inheritance, though, it's not actually considered to be a best practice, really. So there's this phrase composition over inheritance, like favor composition over inheritance. And I think the earliest time this was used was in the Gang of 4 Design Patterns book, this really influential object-oriented programming design book. But now this has just become something that gets repeated by every object-oriented thought leader I've pretty much ever heard of. This is just kind of the way you're supposed to do stuff. It's like, yeah, inheritance is a thing. It's found in pretty much every object-oriented language, but you know what? It's kind of disfavored in favor of composition. I think that's pretty interesting. So that leads me to the conclusion that, if inheritance is one of the uniquely OO language features, which I think it is, it's pretty hard to say that this thing that is recommended not to use as a best practice is somehow explains the popularity of all these OO languages. So I don't think it's inheritance. And I especially don't think this when you think about what are some modern languages that sort of self-identify as being able to support OO paradigms, what do they think of inheritance? So Go is a good example of this because this is a language where they don't really need to have backwards compatibility with any of the other object-oriented languages. Like Kotlin, of course, needs to have inheritance because they want to have really good Java interop. Go doesn't care. I mean, Go is basically trying to be another better C based on using the learnings of the intervening time period, really some of them. And basically Go is you know what? We support an object-oriented style. This is from their FAQ, but they don't have inheritance. They just decided it wasn't worth it. They just didn't want to do it. And it's especially interesting when I look at this in terms of what does that imply for what methods and objects, which are kind of 2 of the other things that I said might be some of the uniquely OO features. And it turns out that once you take inheritance out of the picture, methods and objects are kind of just the same thing as procedures and structs with some syntax sugar. So I think this is kind of true in Go, quote unquote objects and methods are really just syntax sugar. So if you look at these 2 function calls, one is, or procedure calls, circle.grow parentheses 3 and grow parentheses circle comma 3, in both cases, the logic that you're running is this grow logic. And in both cases, grow has access to the circle and the number. So whether or not you write it in method style or whether you write it in sort of procedure call style is really just a matter of syntax. Semantically, the only reason these could possibly be different is if you have inheritance in the mix. So to me, this kind of reduces down to, okay, I've ruled out objects and methods as being uniquely OO. Really, it's just implementation inheritance and or maybe encapsulation. So what about encapsulation? If Go supports an object-oriented style, how do they do that? If they don't have a first-class concept of objects, how do they do encapsulation? So this gets into a sort of broader concept called modular programming. This is
all right. And then next on the list here, if you write the most If you write the most clever program you can, given the unknowns, meaning bugs, it's more complex than you can understand. Now this has particular import because this is one of our fellow Utahns speaking, caught off guard at a meetup.
The strange thing about even really, really smart people is smart people often like to build very complex things. And maybe the constraint of what you're trying to do pushes you to the edge of your intelligence to handle that. But we all know code has bugs in it that you don't think of. So by the definition, if you use all your intelligence to build the most complex thing you can, even though there's a defect in there, by definition, it's more complex than you can understand. Yeah. So it's impossible to debug the thing on your own.
Well, even
I want that on a placard.
So all of this is driving towards something that's really been winning in the industry lately, which is reduced instruction set computing, but for our brains, right? So Apple has gone back and forth on this over the years, but where Apple did something surprising that we all should have realized because we all carry one of these in our pocket, but I don't know if it was obvious to everyone. Apple was building a desktop class computer on a battery-powered phone. They were using a reduced instruction set computer, an ARM CPU, and the whole idea of an ARM CPU is everything that's been mentioned before. Fewer abstractions, less complexity, more optimizing for doing dumber things faster rather than doing smarter things slower. And then also the concept of modularity. So on your phone, you've got a logic processor or a few logic processors. Those are the ARM CPUs. But then you also have an H.265 encoder, an H.265 decoder, an H.264 encoder and decoder, an M4A encoder and decoder. I think that's actually just part of the H.264. So these are your multimedia codecs. You've got a separate chip that is doing the modulation. You've got a separate chip that is listening for the voice. So what Apple decided to do was take lots and lots and lots of discrete components, and rather than trying to integrate them together like an Intel chip, where one chip can do any task really well as long as you don't mind it being burning hot, they separated all the tasks out so that each unit of hardware only handles one task, and it handles it really well. And then you can believe the marketing hype or not, but I think it is non-controversial to say that Apple shook the industry when they released, oh yeah, so that thing that you've had in your phone, we just replaced it with the computer. And yeah, by the way, you couldn't really do benchmarks on your phone because nobody was thinking to create an app for that. But now you can benchmark the phone processor and you can see that it's better than most desktop processors, right? And then they iterated that over the past couple of years and released the M1 Ultra and actually did something quite interesting in terms of being able to align. This is the first multi-CPU outside of the server market that has landed in this space. But I won't go into the details there. I'm getting kind of off track, fanboying a little bit. But the idea is that they were able to create something that consumed so much less power and is more powerful by focusing on less. Okay, so that's number one. So before we leave that, let's take a minute for some discussion. I don't know how to do a 4-hour presentation format. I don't want y'all falling asleep if we can help it. So let's just, I'm going to open the floor. I'm just going to be silent for 30 seconds, a minute here until somebody asks something or contributes some comments or ideas. But within this idea of less is more, what are some things that you've gleaned? What was good or worthwhile? Sometimes the comments are wrong because the code is morphed in a way the comments didn't, because it was not functionally necessary to change the comment to change the code. Yeah. But anyway, what was your name again? Vicky, and then Lauren. Oh, I'm going to help you there. I just need to make sure that at least I've laid a foundation that's a good, rational argument for, you must unlearn what you have learned. That's a bridge too far for me, the no code. But that may be because writing code is my not at all unabashed, unguilty pleasure. But yeah, the remark I'll make on that is that there's obviously trade-offs in all things, and it really depends on where your value is. So are some of you familiar with Clayton Christensen, the business guy? So he wrote a book that's really, really important if any of you are considering the entrepreneurial path, or even if you're looking at consulting for companies, called The Innovator's Solution. You'll most often hear the wrong book talked about because the other book that is more popular is far less valuable because, well, obviously the book that's called The Innovator's Solution has the better material in it than the other book. But one of the things he talks about is vertical integration versus import modularity versus export modularity. And the difference between that is, where is the value in your value chain? So you can look at companies, take two companies that are exact opposite in their business model, IBM and Apple. Apple is always doing import modularity to acquire assets, skills, and technology. So Apple will partner with Motorola and then 20 years later buys them to create their CPUs. Apple kind of has the same Microsoft mentality of embrace, extend, extinguish, but they do it from the perspective of partnering with somebody, getting really, really intimately familiar with their technology, asking for a ton of custom changes, and then buying out or taking over that company to completely vertically integrate their system. And when you vertically integrate something, typically you lose modularity because you're saying we're going to trim the fat on all the things that we don't need. Because if you're exporting, you want to support multiple different types of customers and multiple different types of scenarios. If you're integrating, you can trim the fat. You can say the only scenarios that we care about are the scenarios that matter to our company. And then you can go the other way too, which is what IBM has done, which is they develop technology in-house and then they actually broaden it and then they export it and sell it out to others. And so nobody knows what IBM does because every 5 years, IBM has a completely different business model. And Clayton Christensen explains this, but it's basically this cycling through of developing a technology, finding the fit in the marketplace, exporting it, but then other people are doing what Apple's doing where they're importing it and then integrating it. And so then IBM has to come up with their next model. And Microsoft is kind of somewhere in between. I don't know what Microsoft's doing right now, but they do own GitHub and NPM and GPT-3 and basically everything that a developer interacts with other than the MacBook. So something's going on there. Anyway, a little off topic, but hopefully entertaining and useful. But with that, shall we proceed? Or any more questions or comments or thoughts? Okay. So number two is, so first I was trying to talk about, okay, less is more in terms of the code, but this is a different type of less is more. Less is more in terms of the decision making. So in some circles, this is called Emergent Design, or the word agile is lost all meaning because of the way that it gets used, but you could also say, if you looked at the actual Agile Manifesto, the one that was written by the people that coined the term before it was taken over by all of the training gurus, it kind of speaks to this, but basically it's just delayed decision making. So can we not make a decision? And there's lots of different ways that we can go about doing that. So I'm going to quote again from the Go blog because, gosh, they're just such smart people. Ugh. So this was in reference to a worldwide outage that only happened for a couple of seconds, but it was big enough that it was some Go. Because if you don't know, Go code It's Docker, it's Kubernetes, it's all the internet infrastructure that you use, all of it's Go code. And some of that's being replaced with Rust code and the hotspots, but the internet was rewritten in Go over the period of a decade, which is absolutely phantasmagorically amazing that something had that much sway in the market. So we did what we always do when there's a problem without a clear solution. People had raised this problem, and they just they didn't address it. They didn't say, yeah, we're going to release the next version of Go that has this fixed, because they basically said, we don't know how to solve this problem. It had to do with timestamps and time skew. So, but just to give the context. So we did what we always do when there's a problem without a clear solution. We waited. In the face of ambiguity, refuse the temptation to guess. One of the most important stanzas of all the creeds of craftsmanship. Waiting gives us more time to add experience and understanding of the problem. So we don't want to come up with the perfect solution, because if we wait, it gives us more time to understand the problem and more experience, and also more time to find a good solution. Now, there's not a video clip for this, but if you want to check out the blog, it's from 2017 toward Go 2. There's a lot of good stuff in that article, but this was the nugget of gold that I found in it. Was just this: we chose to do nothing. We didn't know what to do, so we didn't do it. Wow. So at church, we're doing this book club thing amongst the men, and our book this quarter was How Doctors Think. And one of the quotes from the book about diagnosing patients was, I guess there was a doctor or a surgeon, and then there was the assistant. And the assistant, when something seemed to be off, the assistant would say, don't just do something, stand there, to remind the doctor, hey, take a breath, make sure that we're going down the right path. We're not just treating something because there seems to be a way to treat it. Make sure we're treating the right thing. If I remember the way that was portrayed correctly, it was the junior person that had the duty and responsibility of bringing that to the doctor's attention. I may have gotten the other way around, but either way, it holds true in a lot of facets of life. Okay, so this is one that's don't make the most difficult. Don't make the most difficult to change decisions at the start. That's when you have the least correct information to guide it. So I put yours truly on this. It's actually paraphrasing someone in the Go community, but I couldn't find the particular talk. So in regards to this is particularly about typing, framework choices. What framework are we going to use? What inheritance model are we going to use? What kind of polymorphism are we going to use? So if type hierarchy is the foundation of your program, it's often easier to struggle along with an incorrect type hierarchy than it is to change it. So this is juxtaposed to what I said here. So there are certain decisions that if we can somehow delay them, we can make better decisions as we gain more experience. So this was, again, I do apologize that at least half of these, if not more, are Go talks, but they're just so smart. Go!
So if we step back for a moment, if you're coming from Java or C++ or Python, the thing that's missing in this program is a type hierarchy. And in Java and those other languages, the type hierarchy is really the foundation of your program. And you have to put it down before you write the rest of your program. And then when you get halfway through your program, a lot of times you realize, oh, I should have structured it differently. And at that point, it can be hard to change. And in fact, it's often easier to just struggle along with a slightly incorrect type hierarchy than it is to go back and change it. Now in Go,
what is that? So this delayed thinking presents a problem. We get an analysis paralysis. We're trying to find the perfect solution because we need perfect software. So for every metric, a counter metric. That actually should go back in the Axioms of AJ because I say it all the time. For every metric, a counter metric. So no, we cannot typically identify the perfect solution. There's always some trade-offs. There's always some things where we could go down road A, or we could go down road B, or we could go down road C. But the thing is, sometimes people use that as a justification not to make a choice, because at some point either going down road A, B, or C is going to yield good results, but with trade-offs. So the thing that we need to be wary of, that the reason for this delaying decision-making is not necessarily to arrive at perfection, it's this other piece. That although we cannot identify the correct solution, we can identify incorrect solutions. So we can fairly easily tease out ideas that we know are bad. So we're going to have two little segments here from John Oysterhout. So he is the guy that designed TCL. Don't worry, he regrets it. But he's, veteran.
So there are these vague principles. Then the other thing I try and do is talk about red flags. So red flags are very specific things that if you see this sort of behavior or pattern, you're probably in trouble. And actually, I think for beginners in particular, red flags are really useful to people. Because even if you don't know how to design the right system, if you can see you're going wrong, then just try something else until eventually the red flags go away, and you'll probably end up in a pretty decent place.
So we're going to hear more from him in just a minute. Now, here's an old one. Perfect is the enemy of good, 1770. That's roughly when that originates. It appears in the English lexicon. So that one's been around for a while. And then the segment that we're going to look at in just a second is he uses the wrong word because he's an old fogey and he's not hip with the latest language of the day. But so I put in the correct word that he actually clarifies this later. But abstractions should be deep, and he's going to do a great job showing you what he means by that. A shallow abstraction does not help you in the fight against complexity. So this is kind of moving in a different direction in terms of another metric where we want to delay decision making. A lot of times we start wrapping things and wrapping things and wrapping things. I recently had to work with some cryptographic signature code where I had to go through 4 different libraries of C++ code that had every possible way of overloading something. The function's defined 15 times, and at the end, it was about 5 lines of C code that was actually being run that I actually needed, but I had to go through the constructor, and I had to go through the validation, and I had to go, and I had to go, and I had to go, and it took a really long time to essentially pull out 2 to 3 lines because there was all of this shallow abstraction in the way. So we've got 2 segments here. I might just skip ahead a little bit on this one.
Matters a lot. You want to make
that's weird.
This is really just another way of thinking about this idea that the idea of information hiding that David Parnas first put out in a paper in the early 1970s. By the way, to me, this paper is one of the 2 most important classic papers in all of software design and engineering. Has anybody here read this paper in classes? Great. It's still topical and relevant today. The last third, maybe not so much so, but the first part still, and it's got a great example and easy to read. So the way I think about it, think about a class as a rectangle. And the area of the rectangle is the functionality that class provides. So you can think of that's the benefit that the class provides to the rest of the system. Then think about the top edge as that's the interface to the class. And by interface, I mean everything someone has to have in their mind in order to use that class. It's not just the signatures for the functions, but things like side effects and dependencies and things like that. That's really the cost. You think of that's the complexity cost that this class imposes on the rest of the system. So we'd like that to be as small as possible. So ideally, what you'd like is the greatest benefit, least cost. So you'd like the smallest interface and then the largest area. So the opposite of that I call a shallow class. So that's something that has either not a whole lot of functionality or a really, really complicated interface or both. Those classes, they just don't give us much leverage against complexity. In fact, in the worst case, the additional overhead of the interface adds more complexity than what you've hidden underneath the interface, and it's a net negative. What we'd like to have, of course, on the other side, is a deep class. Very simple interface with a very large amount of functionality underneath it. Here's a classical example of a shallow method, which I have to say I see distressingly often. There is essentially no information hiding in this method. In order to use it, you pretty much need to understand the complete implementation. And by the way, there's almost no implementation there. In fact, this is so bad that it takes more keystrokes to invoke the method than if you just did the body of the function yourself. So it's basically a complete loss, just adding complexity and getting nothing back for it.
So this is the example that he showed on the screen. By the way, if you do have a Mac, there's this amazing utility that uses the new text recognition where you don't have to make a screenshot first and then open it. You can just do Command-Shift-2 and then. So I actually screenshotted the video and then copied and pasted this. So it's called Text Sniper. If anybody's interested in that, so if you want to, next time you're watching conference talk, oh, I want to run that code that's on the slide. You use Text Sniper, or you can take a screenshot and then open it and then select it. But Text Sniper puts it directly in your copy-paste buffer. Anyway, so just I think everybody could see this before, but I literally, so I do code reviews, and I am the worst person in the world. You would never want to have me doing code reviews with you, because I snipe at all these things. And one of my coworkers did the exact same thing as this. Obviously, it was a different method name, but he did the exact same thing, where he took a bunch of places where there was 2 arguments to something, and one of them could be a default argument or something like that, and then he wrapped a function around it, and then gave it a longer name. It was this. I denied that pull request. Well, there were other parts of it that were good, but I had a change request for that. Anyway, so and this is just some AJ wisdom here. So we didn't actually show the part of the clip, but he asks, how do we discern a metric for how deep something should be or how wide it should be? Because you hear all these basically every buzzword that you hear is taken out of context and abused and doesn't mean what it meant. Right? So dry, don't repeat yourself. You see people in the Rails community writing one-line functions so that they never repeat a function, but then they have this, and then that's what they're repeating instead of the thing that they're, and then, so there's all these different buzzwords that get thrown around, and they get taken to the extreme. And it's hard to put a number on something, because you say, oh, well, a file should only be this many lines long, or it's just hard to quantify these things. And so I've got 2 guiding principles in regard to this. One is that the body of a function should fit in a single scroll more or less. So by single scroll, I mean I should be able to, whatever size I'm accustomed to with my code editor, and I expect people in my team to be working on in their code editor, and what I'm able to see on GitHub, et cetera, essentially what's going on in that function should be able to fit in a single screen. If it goes over a couple lines, whatever, but we shouldn't be trying to, let's make sure that none of our functions are more than 5 lines long. I mean, there are some pedantic metrics I tend to follow myself, but yeah, this is just a good idea, I think. And then the functionality of a module or a package should fit in a file, more or less. Now, this one's a little contradictory because, well, how long is a file? Well, as long as you need it to be in order to get the functionality in there. I don't know how everybody else works. I imagine it must be differently than me, because I go on GitHub and almost every JavaScript project I see is 1 function per file. And I don't know how y'all deal with this. I'll open this up for comments in just a second. But for me, that's insane, because when I use grep to go search for where something is, I have to go through 10 different files to figure out where's the actual implementation. If you've got a group of code that's related together, who cares if the file is maybe 2,000 lines long? If you're getting to 10,000, maybe that's a little too long, but maybe it's not. You should be able to group related functions of a package together. JavaScript doesn't really have a nice way of breaking that down, and so people just go to the extreme and do 1 function per file. In Go, you can kind of, you can have a folder. A folder is a package in Go, not a file, and so you can put some things adjacent that, these 500 lines really seem to go together, and these 500 lines really seem to go together, and this is kind of the MISC stuff. But anyway, this is just, a general guiding principle is that you should be able to fit stuff that is related to each other, tightly related to each other, should be able to go in a single file and single module. So we'll talk about that more later. And then this concludes part 1. Good enough for now. But who has not had the moment when you think, who was the idiot that wrote this? And you do a git blame. I don't remember writing that. That was not me. That somebody made a white space change and got my name on it somehow. No, naming things is hard. But I do want to remind everybody in the room, naming things is billable time. When you sit there thinking for 5 or 10 minutes, what should I name this? Sometimes you're being pedantic, but sometimes it's really worth taking that 5 or 10 minutes to think, what is this doing? And a lot of times that is an indicator that you have gone either too shallow or too deep if you can't name something well. I think okay. Let's put it this way. I think you should be able to discover within 5 or 10 minutes whether or not the reason you can't name, if you can't name it within 5 or 10 minutes, I think the reason is that your abstractions are going too deep or either too narrow or too broad. Your abstractions are one direction or the other. Because almost every single time when I can't name something, it's because I'm doing 3 things, and so no one name suffices. Now, I will admit, on occasion, I have called something do stuff because literally this is what the code has to do. Breaking it apart doesn't make it any simpler because you end up with the same thing that I was just showing earlier where you've got, okay, you broke it apart to call the 3 things that happen together. Each of them can be named independently, but if you name them independently, then you got 1 or 2 lines of code. But when you put them together, maybe you only have 10 lines of code, but you can't name it. So yeah, there's contradictions. There's things that we have to make trade-offs on. But again, the goal is to get in a direction and improve as we go. And certainly over the course of 5 years, as you were saying earlier, your opinions are going to change. Your belief systems are going to change. Your tool set is going to change. So you're not going to have perfect consistency. If you do, then you're not learning anything. And well, maybe that's worse. So there's that. I agree. There's some things that are unavoidable. There's sometimes we're going to make decisions. We just have to. So yeah, 100% agree with you. We don't want to get stuck in analysis paralysis. A poor decision violently executed is more profitable than a perfect decision never executed, or however that war general said it, something similar to that.